All right, everybody, welcome back to Calculus 3 for our final class of the semester. So as advertised last class, what we're going to do today is we're going to continue through our quest to finish the spring of 2018 final exam, which was also non-cumulative and also about this last section of material. Now, a lot of people are definitely confused. So we have this sheet that's provided to us on the final here, and it has all of the different iterations of the fundamental theorem of calculus, or as I revealed in our last lesson, generalized Stokes theorem. Now, there's a lot of these, and a lot of them have the same type of integral to them. In particular, 4 of them have some sort of variety of surface integral in there. So that kind of begs the question, which one do I use when? And the answer to that is, if you can use one of these, it's probably a good idea to use one of these, because usually transforming over to the other version of the integral will end up making whatever integral you have easier. So for example, if you're tasked to do maybe like the surface integral of a curl, at least consider trying to do the line integral along the boundary curve. Or if you have to do a flux integral like this, at least consider over a closed surface. There really should be a circle here. Yeah, if you have something like this, you should at least consider using the divergence theorem. The divergence theorem in particular almost always makes it way easier to use. So the answer to that question is, when should I use these? And the answer is whenever you can. All right, so I think last time we left off at number 11, and I actually, so on 11 here, I think I mentioned last time I made a mistake. I originally said this was 0 because I was so tempted to use the divergence theorem on this, because the divergence of the curl is 0. But I neglected to remember that this was not a closed surface. This is only this paraboloid kind of draping down over the XY plane here. But it doesn't have it. This disk at the bottom is not filled in. We don't actually have that. So it's not enclosing some sort of volume right here. All right, so let's go ahead and actually do this here. So we can't use the divergence theorem for this. So I guess we'll just go ahead and do this in the old-fashioned way, the straightforward way. The first thing we need to do is we need to compute the curl of our vector field here. All right, so let's go ahead and do that. So the curl of F, we have I, J, and K. We have our X derivative, our Y, and our Z derivative. And then we have negative Y, X, Z. Okay, well, let's see what we get for this. So for the I component, we do the Y derivative of Z. That's 0. And then we do the Z derivative of X. All right, well, that also seems to be 0 here. Okay, next we have J. We do the X derivative of Z, which is 0. And then we do the Y derivative, or sorry, the Z derivative of negative Y, which is 0. And then finally, for K here, we do the X derivative of X, and then we subtract the Y derivative of negative Y, giving us 2 right here. Okay, so we got that. Oh, actually, wait a minute. So we could do it this way. Now I'm realizing I'm not taking my own advice. So if we ever need to do a surface integral that's a curl, we may want to consider flipping it over to the line integral right here. So if we need to do a surface integral that's a curl, and it looks like we have this situation here, then perhaps we should do a line integral around the boundary of the surface. So since the surface kind of extends down here, the boundary of the surface will be this circle kind of going around. And since this is positively oriented, we can imagine we have a little person in the same direction as our normal vector right here. And when they're walking around in the correct way, the area should be to their left. So in order for that to be the case, we need to go counterclockwise. So we need to parameterize this circle. 0 is 4 minus x squared minus y squared, or x squared plus y squared is 4. We need to parameterize this circle and then integrate this along the circle. Although the way this was going, this actually wouldn't have been too hard of a surface integral. Now I'm looking at this. So we could have done this one directly without getting punished for it. But I think it's probably better for us to try to use the line integral here. All right, so I'm going to parameterize the circle, and that's something we've done many times. So r of theta, and it's a circle of radius 2. So we have 2 cosine of theta, 2 sine of theta, and then z is 0 since we're in the xy plane. Okay, so rather than doing this, I'm instead going to attempt to do this. So we have f dot dr, and we're going around our closed path. Okay, well, we're going all the way around the circle, right? So our theta will range from 0 to 2 pi. Next, we have f as a vector field. So let's see. So we have our nice parameterization for our path. Let's substitute that in to our vector field here. So we have negative y, which will be negative 2 sine of theta. Then we have x, which is 2 cosine theta. And then we have z, which is 0. Okay, next, now remember the way we compute these, we don't have just dr on its own. Remember that dr is r prime of t dt, or I guess theta in our case. So r prime of theta here will be negative 2 sine of theta. And we have 2 cosine of theta, and then 0 right here. All right, so we're going to dot it with r prime of theta, which I just wrote. All right, so then let's see what this dot product produces. All right, we have negative 2 sine theta times the same thing. So we have 4 sine squared of theta. And then we have 2 cosine of theta times itself. We have 4 cosine squared of theta, and then 0 squared. All right, once again, we have a Pythagorean identity appearing. This is going to be 4 right here. So I'm simply doing the integral of 4 d theta from 0 to 2 pi. And remember, when we integrate a constant, we simply just multiply by the difference between these numbers. So this is 4 times 2 pi, which is 8 pi, exactly as Pastian predicted here on the sheet. We end up getting 8 pi. Although actually, yeah, starting to do the surface integral normally, it seemed like this one wouldn't have been too bad. But usually using one of the integration formulas here will make things easier right here. Let's see. So why is it sometimes when we do these problems, you have to do the integral over the paraboloid plus the integral over the circle? But here we only needed the circle. You may have been thinking about a time where we wanted to do a surface integral where we went over the paraboloid and then we went over the disk. So if you ever want to do a surface integral directly over a closed surface, then you may need to break that up into pieces. But I was just going around the boundary of this one surface here. So I didn't need to do that in this case. All right. Can you explain the difference between f dot dr when dr is not a vector as opposed to f dot dr when it is a vector? Yeah, so that's the difference between vector line integrals and scalar line integrals. This is a vector line integral. And then a scalar line integral would be f, and a lot of times it's written like this, ds. And this is going to be, ds is the square root of x prime squared plus y prime squared plus z prime squared dt. So it just depends on what your parameterization is, what your ds is going to turn into. All right, why is r of t only need one variable? Because it's for a curve. So it's a one-dimensional object. We're just spinning around here. It's just a curve. So we only need one variable for curves. And we need 2 for surfaces. Okay, next we are provided with a conservative vector field. Okay, that's nice. They don't tell us what it is though. Let's C1 be parameterized by R1 of t equals cosine of t sine of t with 0 ranging from, or t ranging from 0 to pi. All right, so what's that? Well, if we draw that, so this is the parameterization of the unit circle, and we're going from 0 to pi right here. Okay, so that's our C1. This is C1. Okay, let C2 be the line segment from 0, -2 to -1, 0. So we're going from here to here. So the arrow will actually point this way. That's C2. And then C3 is parameterizing this ellipse going from -π/2 to 0. So it's going to go from here to right there. So it's going to go this way right here. So this is C3. Okay, now what they're saying here is that if we do the line integral of f dot dr along C1, we get 4. So we get 4 if we go this way. The line integral along C2 from here to here will be 3. So if we go from here to here, we'll get a line integral of 3. Now what they're asking is if we do the line integral along this last segment here, what will that be? So remember what this line, or this is not a line segment, remember what this curve is doing. This curve is a path from 0, -2 to 1, 0, right? Now recall that this was a conservative vector field, probably the nicest variety of vector fields we can have. So one property about conservative vector fields is known as path independence. So what that means is that if we go this way from this point to this point, that's the same as going all the way around here from this point to this point right here. So it doesn't matter which path we take through our vector field. If we go from point A to point B, the line integral will be the same regardless of the path. So we don't really know anything about this, but we do know what would happen if we went along here. So as we go from C2 to here, that's going to give us 3. Now let me ask you this, as we go from here to here, what will the line integral give us for this last leg of the journey here? Very good, that's right. It's not going to be 4, it's going to be -4, because as we're traveling along this, we're going in the opposite direction of its orientation. So when it's positively oriented, it has a value of 4, meaning if we go the opposite way, it's going to have -4. So we have 3 here, -4 here. That combined will give us -1. So that's going to be the value we're going to get from the line integral going from here to here, because this vector field is path independent. So we're going to get -1 for this one right here. Oh yeah, that's another good idea. Yeah, that's an interesting way of thinking about it. So Michael is suggesting that we could do 4 plus -3 plus C3 is 0, because since this is a conservative vector field, if we start and end at the same point, our total value will be 0. So if we add up what we get along this way, which will be +4, and we get -3 going here, and then we have C3, so 4 minus 3 plus C3, we'll end up back where we started, meaning that we're going to have 0. Yes, that's another way of thinking about this here. Either way is fine. All right. Is the sum 0 because it's conservative? That's right, because if we made a potential function for this vector field, which we can because it's conservative, we would plug in the same point to it twice. So then f of b minus f of a would be 0 here. Yeah, Tristan, I think you're kind of effectively saying this right here. All right, so that was a good one. Use conservative vector fields. All right. Can you not just make a line between the second and between the two and find its length? Well, remember, we're not measuring length right here. We're doing the line integral. So we're doing f dot dr. So we're not saying that this path is a length of 3, this path is a length of 4 or anything. These are the values of integrals over these paths. So drawing a path like this and figuring out how long it is won't necessarily make things any easier. Although, in fact, if we did draw this path, so if we did draw a line segment here, then the line integral, this would also be -1. Because remember, this is path independent. So this line segment would also have a value of -1 if we did the line integral of that. All right. Let's take a look at the next one here. Let E be the set of all x, y, z, such that x squared plus y squared plus z squared is less than or equal to 1, and z is greater than or equal to 0. So this is the unit ball with non-negative z. All right, so what's that going to look like? So we have a circle in the XY plane. And we have this. And it's going to be filled in. So it's going to include everything inside here because we have x squared plus y squared plus z squared less than or equal to 1 right here. Okay, so what do we have to do with this unit ball, or half of a unit ball? Which of the following describes the boundary of this ball? So remember, the ball itself has everything filled in here. The boundary will be the surface enclosing this volume. So the surface enclosing a unit ball is going to be a unit sphere in some way. So what we're going to have is we're going to have the unit sphere. This time it's going to be hollow. And then we also want to fill in the base here to kind of cover up the bottom of this. So we have two pieces. We have the unit sphere on top, and then we have a disk of radius 1 here on the bottom right here. All right, so let's see which one of these represents that. We can honestly kind of narrow it down to these two right away because we're having the union of two different pieces kind of glued together. So it's likely going to be one of these two. So if we look at this one, and I already kind of spoiled it by circling this. Here we have the unit sphere because we have x squared plus y squared plus z squared equals 1. And then this is restricting it to be the upper half of the unit sphere. So this part gets the unit sphere. And then this part right here gets the disk. So the disk is the circle with the inside filled in. X squared plus y squared is less than or equal to 1 right here. And then z equals 0 because we're on the bottom of this. So that's why this one's going to be correct. This one's almost correct. You could have said something like this. That would have been okay. But then this part is definitely messed up because we don't have a less than or equal to right here. So the boundary curve would be like wrapping a present. Yeah, well, this is boundary surface, but yeah, that's right. So imagine if we have a unit ball, like we cut like a pool ball in half or something, and for whatever reason we want to give it to somebody, we're going to wrap this present. And the surface that the wrapping paper makes will be this right here. So yeah, that's a good way of thinking about it. Okay, next we have number 14 here. Find the work done by the force field yzi hat, xzj hat, and xyk hat in moving a particle along the curve cosine t, cosine squared of t, and then cosine to the 5th of 2t from 0 to pi over 2. Okay, so this right here is kind of discouraging me from doing this directly. Because remember, we learned what work was. Work is going to be the line integral of f dot dr along the path right here. So I don't want to do this directly because then I would have to start throwing in cosine to the 5th every time I had a z, which I do have. And then I would probably end up integrating something like cosine to the 7th, cosine to the 8th. And you guys pass Calc 2, you know how unpleasant that would be. So we don't want to do that. So what I'm going to do, if I don't want to do it directly, I'm going to pull out my sheet here and I'm going to see if any of these might help me. So let's see here. We're not going around a closed surface or anything, so I guess we can't use these. This is for Calc 1, just kind of for reference. But maybe we could use something like this. So if we can get our line integral to be the line integral of a gradient of a potential function, then we could simply just plug in the starting and ending points. So that would require our vector field to be what? What kind of vector field are we hoping for here? Oh, yeah, Ryan's already got it. That's right. It's got to be conservative right here. So we're hoping that this vector field is conservative. Okay, if it's not, then unfortunately we're going to be stuck integrating cosine to the 8th or whatever. Okay, so what I'm going to do, I'm going to integrate each of these components with respect to their matching variable and see if we can get all of that to match up. So I'm going to integrate, if this is P, Q, and R, I'm going to integrate P dx, which is yz dx, which will be xyz plus a function that could depend on the y and z only. For q, oops, well, let me write q. For Q, we get this. And once again, we have X, Y, Z plus maybe something that depends on X and Z only. And then finally, let's do R with respect to Z here. So we have X, Y, D, Z. So once again, we have X, Y, Z plus G3 of X, Y. Okay, well, it seems like we only got one significant component from all of these. So it seems like our potential function is going to be X, Y, Z, and then maybe we have some constant here. But since we're doing an integral, it doesn't really matter what that constant is because it's going to cancel out. So we can kind of just forget about that. So our potential function is X, Y, Z. All right, so then that means all we need to do is figure out what our starting and ending points are and then plug them in to our potential function. All right, well, they gave us our parametric curve and they gave us the starting and ending t values. So let's use these. So our point A is going to be when t is 0. So that will be the point, let's see, 1, 1, and 1. Okay, so our point A is 1, 1, 1 right here. And then B, we have pi over 2. We plug that into here. We have 0. We have pi over 2 plugged into here, which is 0. And then we have pi over 2 plugged into here, which will be cosine to the 5th of pi. Cosine of pi is -1. So if we raise that to the 5th, that will be -1 right here. Could I also say that f is cosine to the 8th of t? Well, it wouldn't quite be that because this has a 2t here. So that would kind of mess things up. How did I get A and B? I'm plugging t equals 0 into here, the starting point. And then I'm plugging in t equals pi over 2 into here. And that will get me the ending point right here. How do I know this isn't closed? It's because A and B aren't the same thing. So if A and B were the same thing, then we'd be going over a closed loop. And if this was still conservative, then we would automatically have 0. All right, so now we're ready to finish things off. Our work integral, f dot dr, is the same as line integral of a gradient, which by the fundamental theorem of line integrals, as we saw on the sheet, this will be f of b minus f of a. All right, so what's f of b? Well, f of b is going to be 0 because we have at least one 0 here. And then f of a, we have 1 times 1 times 1. All those multiplied, they'll just be 1. So we end up having some negative work here. We end up having -1 of work here. How did I determine to use the potential function again? If I remember computing work, it's easier to compute work this way than doing the line integral manually. So I'm going to check to see if it does have a potential function, because conservative forces are much nicer than non-conservative ones. You could say that f is cosine cubed. Yeah, you could write the potential function in terms of t though, although that's kind of bad form because this is independent of any parameterization of any path. Whereas if you plugged in t, that would be dependent on that particular path. So it's not wrong to do that, but it's not as good as having this formula right here. All right, so we got number 14, so that was good. So we're using conservative forces to help us compute work right here. All right, let's go to this next problem here. Evaluate the line integral over C of y sine of z ds, where C is the circular helix given by this parameterization. And we're going around the helix twice, it seems, because we're going from 0 to pi over 4. Okay. So let's see here. This is actually an example of what I was talking about earlier today. This is an example of a scalar line integral. Because everything in the integral, you can see there's no vector symbol anywhere. This is simply a scalar line integral. All right, now they were kind enough to give us our parameterization already, so we could begin substituting that immediately into here. So we know t will go from 0 to 4 pi. Y is sine of t. And then we have sine of z, but z is just t. And then we have ds. Now, earlier I mentioned what ds was. ds is the square root of x prime squared plus y prime squared plus z prime squared dt. All right, so we can compute what that is. Let's see, the derivative here is negative sine, and when we square it, we have sine squared. The derivative here is cosine, and then when we square that, we have cosine squared. Okay, this is good. I have a Pythagorean pair. And then when we do the derivative of t, it's just 1, and 1 squared is 1. So when all the dust settles after our Pythagorean identity here, this is 1 plus 1 is 2 under square root. So ds is going to be the same as root 2 dt right here. Okay, so that's the integral that we're going to have to do right here. Okay, well, another way of writing sine t times sine t is, of course, sine squared of t. So this is root 2, 0 to 4 pi, sine squared. All right, and let's dig back some memories from calculus 2 here. How are we going to do the integral of sine squared right here? The half angle identity is correct. Oh, is ds the same as the magnitude of r prime dt? Yeah, that's literally what I did here. Yeah, so this is the magnitude of r prime here. Yeah, so that's another way of thinking about it if you want. Yeah, we're going to use the half angle identity. So I'm going to move the half from the half angle identity out here. And then we have 1 minus cosine of 2t dt. Integrating this gives t minus sine of 2t over 2. And now we're going from 0 to 4 pi right here. All right, so let's see here. I plug 4 pi in. So I have 4 pi there. I plug 4 pi into here, that gives me sine of 8 pi, but that's just 0. I plug 0 into here to give me 0. I plug 0 in there to give me 0. So when all the dust settles after this cancellation, I end up with 2 root 2 pi, as indicated here. All right. So there we go. So that was an example of doing a scalar line integral. We find the magnitude of r prime to make like what we kind of referred to earlier as like our Jacobian in quotes. So this is like, you can imagine this as a Jacobian from switching to t. And then we just did this integral with t. All right, let's see here. Next, on the previous question, how could we use the formula without having the gradient? Oh boy. So I'm guessing you're talking about number 14. So if we were masochistic, we could have done this one by finding out what r prime is, which would have been negative sine of t. What is this going to be? Negative 2 sine of t cosine of t. Oh boy. And then this is going to be negative 10 cosine to the 4th of 2t sine of 2t. We would have then dotted this with this right here with all of these substituted into here. And then you can end up seeing where all these massive powers of trig functions would be coming from right here. So it's technically viable to do it this way. It's strongly recommended that you don't do it that way, unless you want to use the whole test to do it that way. All right. Let's see here. Dr. Manley, when we use the divergence theorem, we would use the divergence theorem when we have some kind of closed surface integral that we think we can maybe make easier by turning it into a triple integral. So if you're doing the flux of something across a closed surface, that's a good time to use the divergence theorem. All right, this is one of those which of the statements are true questions. Suppose F is a vector field with continuous second partial derivatives defined on R3. And remember, R3 is a simply connected open and closed region. Which of the following must be true? All right, so remember, this is just a generic vector field, right? We don't really know anything about it. We don't know its formula. It doesn't say it has any special properties or anything like that. So the first statement is that the curl of F has to be 0. What do you guys think about that? Well, I guess I kind of spoiled it. I probably shouldn't have done this. I probably should have wrote this, but okay. So it seems pretty clear that P is not going to be true. Why is that? Why doesn't the curl have to be 0? Yeah, we don't. Yeah, Ray Deep has the right answer. We don't know the vector field. Yeah, and not all vector fields have a curl of 0, of course. Otherwise, curl would be kind of a silly concept. So since we have no idea what this is, we don't know if its curl is 0 or not. If it said it was conservative, we did see that conservative vector fields have a curl of 0, but they didn't say anything about that. All right, Q. If the divergence of F is 0, then there is a vector field G such that F is the curl of G. All right, so I think we talked about this statement on the day we introduced divergence here. So does this have to be true? Well, again, I guess the answer is yes. And reason is that if you do the divergence of the curl of something, remember the divergence of the curl will always be 0 without a vector symbol. And then we talked about the converse of the theorem. If this is true, does it have to be the curl of something? And the answer was yes, so long as we're in a simply connected region right here, which we are because we're on R3. If we were on R3 and then maybe we had like a line taken out or something, that wouldn't necessarily be true anymore. But we're just on regular old R3, so that is true. Finally, we have the statement that the curl of F is always 0. So there are a lot of interesting kind of relationships between curl and divergence and when you apply them to themselves and things like that. But curl of the curl isn't one of them. That's not really something that's automatically going to equal 0 for any reason. So that one's not necessarily true. I'm sure there are vector fields where that is true. But yeah, it doesn't have to be true in general right here. What is the curl of the curl? Oh, geez, there's like this really nice kind of formula for it in terms of the del operator, but I totally forgot what that is. I've done physics before. I don't ever remember a time where I've done the curl of the curl, but I don't know. It's definitely not 0 all the time. I can tell you that. If we didn't know that off the top of our head, would you recommend that we try and find a counterexample? Yeah, so you could just pick some probably non-conservative vector field, and you could just kind of give this a try and see if you don't get 0. Yeah, so if you were unsure about this one, you can kind of come up with a random vector field to try. And actually, a good thing to do, so we've definitely seen some non-conservative vector fields on this exam. We can just try on one of those rather than make one up ourselves. All right, so it ends up being that this is going to be Q only. All right, next we have 17. This is asking about this vector field. It was an arbitrary vector field. So in order for those statements to be true, they would need to work for all vector fields F, or defined over R3. So if we even find one where it doesn't work, then the statement is false. That's called finding a counterexample. All right, Stokes theorem. Use Stokes theorem to set up an iterated double integral for this line integral if this is our vector field, and C is the positive oriented curve of the intersection of the plane Z equals X plus 1 and the cylinder X squared plus Y squared equals 1. All right, let's draw this real quick. So the cylinder, we know what that looks like. It's going to be the circle, the unit circle here. It's going to go up. Now the plane Z equals X plus 1, that's going to kind of slant this way. So we're going to kind of have it come in diagonally like this. So it's going to be kind of a cylinder, but then it has a diagonal cut through it. And what we're looking at with the intersection curve is we're looking at this circle right here, this sort of tilted circle right there. All right, so let's see here. So they want us to use Stokes theorem. All right, well, let's get out our sheet and look what that is. Stokes theorem is where we can replace this line integral, which is closed because it's going on in a loop here. We can replace this line integral with the curl of f dot n hat. All right. Well, let's see. Let's go ahead and figure out what the curl of f is, first of all, because we're going to need that. Okay, we have I, J, and K. We have delta x, delta y, del z. And then we have x plus y, negative yz, and xz. All right, what will our curl be giving us now? Let's see. We have the y derivative of this, which is 0. We have the z derivative of this, which is negative y, but then it was the second one, so it's going to be positive y. We have the x derivative of this, which is z. We have the z derivative of this, which is 0, and then we negate that. So we have negative z. And then finally, we have the x derivative of this, which is 0, and then the y derivative of this, which is 1. So we end up with this as our curl right here. So this is the curl of f. Okay, so now we have the curl of f. Now what we want to do is we want to parameterize the surface that this is a boundary of. And what is the surface? It's this right here. It's the stuff enclosed by this loop right here.
Mr. Manley, isn't the z negative 1?
Let's see. Where did I do that? Which component was this for? The last one? Okay. I have the x derivative of this is 0. And then I have the y derivative. Oh, it's negative 1. Thank you. Yeah, because it's the second one. Thank you very much. All right. So anyway, so that's our curl for real this time. Now we're trying to do this integral over this surface right here. So we should probably try to parameterize this surface. So let's see. I'm going to parameterize this since this is kind of like a disk. Whenever I have some kind of disk-like thing, a good choice of parameters for that would be r and theta. I'm going to try r and theta for that. Okay, now let's see here. X will be r cosine of theta. Y will be r sine of, oops, I don't need a y. R sine of theta. And then does anyone know what z is going to be? What's z going to be here? It's going to be r cosine of theta plus 1. That's right, because x is r cosine of theta, and then we just add 1. Very good. Okay, so there is our parameterization of r. Now, as usual, we want to do r. I hate saying that, r cross r theta. So, and then that's going to give us our normal vector for this. So r, what will that be? Cosine of theta, sine of theta, and cosine of theta. All right, how about r theta? That will be negative r sine of theta, r cosine of theta, and then negative r sine of theta. Okay. And then, oh, that is easier. Okay. Yeah, so some people were just using, some people were parameterizing this surface by using the fact that z is a function of x and y right here. Oh yeah, that actually would be, that would be a fair bit easier. Then we could switch in the polar coordinates once we're there already. Oh boy. Okay. Yeah, I just have such a reflex on seeing something circular. I immediately want to use polar for this. Okay. All right. That's actually probably a better way. So you could do it this way. This isn't wrong. And we were almost there actually, but I'm not going to do that. I'm instead going to parameterize this as R of X and Y. That's a good idea. We're going to have X, Y, and then X plus 1. Okay. And then we could use the fact that our normal vector is going to be negative the X derivative of this. So negative 1. Negative the Y derivative of this, which is 0, and then 1. Right. So there is our normal vector. Okay, so now that we have the easier route of doing this, we can go ahead and put this in to our formula for the curl, or our formula for the surface integral. So this will be, let's see, the curl was this, y, and then negative z now is going to be negative x minus 1. We have negative 1, dotted with negative 1, 0, 1. And this will be dy dx. Okay, and then when we do our dot product here, we're going to have negative y minus 1. But because this is a circular region, it's more natural for this to be in polar coordinates. And it's also required because all the answer choices are that way. So if we turn this into polar coordinates, we're going to have an extra r, and then y is negative r sine of theta minus 1. dr d theta. And it seems like there's only one of these that has that integrin. It's going to be right here. But let's just do the bounds anyway. This is kind of enclosed within the cylinder, right? And the cylinder is defined by a circle of radius 1. So this will go from 0 to 1 and 0 to 2 pi. So there we go. We would have actually gotten that answer directly if we would have done this, but it's, yeah, I think it was still quicker this way. So thanks for spotting that. How do I get the normal vector again? Whenever you have z as a function of x and y, this is definitely an important one. So whenever you have a z as a function of x and y, you can use this parameterization, x, y, and g of x, y, if z is a function of x and y. Oh, the normal vector isn't that. And then the normal vector will be negative gx, negative gy, and 1. So you can always do that if you have z as a function of x and y. Why do we not use the equation for the cylinder at all? Well, we sort of did. We used the fact that it's bounded within the cylinder right here to get our polar bounds right there. All right, we have a few more questions here. Next, we have a vector field shown graphically here. Determine the sign of the divergence at the origin and at 8, 8. Okay, well, let's take a close look here. So we draw a little circle around here. Let's see what the arrows are doing to the circle. Seems like all of these arrows, they're relatively big near the origin, and it seems like they're kind of piercing inwards like this. So what does that tell me about the sign of our divergence here? What is the sign going to be? It's going to be negative. That's right. So when we have arrows piercing into our surface, we have negative divergence. All right, now let's go to 8, 8. This seems to be the opposite situation. We have these rather large arrows, and they're all piercing out away from the point 8, 8. So this is going to be positive divergence here and negative there. And so that gives us this answer here. All right, so that was a pretty easy one. Just need to remember what divergence meant. All right, just two more questions here. By the way, they said to ignore 21 through 24. Those are actually just problems in the previous exams, and that none of that stuff will be on this exam. All right. Let's see. Let this vector field be the velocity field of a two-dimensional fluid flow. If D is the semi-annular region in the upper half plane between those two circles with a positively oriented boundary, then the flux of F across this curve is equal to what? Okay, so we want to compute flux here and take a careful look at our line integral. This is a bit different from the other ones. Usually we have f dot dr, right? But this is f dot nds, or you may see this as ds with a little vector symbol as well. What this wants is it wants the flux coming out of this boundary right here. So if we want to see how stuff is radiating out of a boundary, we're going to use the divergence theorem. But since this is only 2D, we're going to be using the 2D divergence theorem, or as it's called, Green's theorem, the flux form right here. So if we have a line integral that looks like this, where we're dotting with a normal vector instead of with dr right here, then we're going to switch it in to this form here. So I want to do the double integral of the divergence. Divergence of f dA over the surface. All right, so what is the divergence? It's the x derivative of the x component, which will be y, and then the y derivative of the y component, which is 2y. Okay, so then we just have the double integral over this region of 3y dA right here. All right. So we have this, and then now we want to change this. It seems like all our answers are in polar coordinates, and reason being is that we have an annulus here, which has circular symmetry here, so we want to use polar coordinates. So if we change this to be polar coordinates, we have 3 times y, or 3r sine of theta, but then remember the cost for using polar coordinates is to gain an additional r. So this will be 3r squared sine of theta. And that's the only one with that integrand here, so we immediately know it's right. But since we're going between circles of radii 1 and 2, and we're only on the upper half of this, those will be our bounds right here. Integrate over the mustache. Yeah, I guess so. And explain why it is n on the test and n hat on the reference sheet right here. Let's see here. Yeah, one of these is not. I think it's this one that's messed up here. I think this one should be an n hat. Because kind of like with surface integrals, this is like the matching version for surface integrals right here. So we have n hat and then we have ds right here. Why can we use those interchangeably? It's because, like, for example, with the surface integrals, if we have n hat ds, that's going to be n hat times ru cross rv dA. And what is n hat? It's going to be ru cross rv over its magnitude, because it's a unit vector. And then I have the unit vector up here, or I have the magnitude up here. So then those cancel out, and this is a normal vector without the hat right here. That's why we kind of flip back and forth between those two. This little work right here kind of enables us to flip back and forth. All right. Now our final question here, and this one was honestly pretty tricky, so let's think carefully about this. Which of the following is correct? And this has one of the dreaded all of the above are correct. If f of x, y, z is 1, 0, 0, then the flux of f across the yz plane is 0. I think we should draw a picture for that one. Okay, so the yz plane is this right here, right? So this is the yz plane. Then what's going on here? So we have all these vectors, but this is a constant vector field, right? All of the vectors are just pointing 1 in the x direction. Okay, now it seems like these vectors are piercing through this surface, right? So there's no way we can have a flux of 0 for this, because we have all these vectors and they're piercing through the surface. They're all perpendicular to this surface. So there's no way this is true. And that actually eliminates this one down here too. All right. B, if S is a surface parameterized by R of UV, then the vector RU cross RV lies in the tangent plane of S at a given point. So this statement is almost true. The only thing that's wrong is that this vector is perpendicular to the tangent plane of S at a given point. Remember, there was a few questions in the beginning when we were doing surfaces right here, where, what was I going to say? Yeah, where we had to find the equation of the tangent plane to the parameterized surface. The way we did that was we used RU cross RV as a normal vector. But if it's a normal vector, remember this is n. If it's a normal vector, it's not going to lie in the plane that it's normal to. So that doesn't make any sense. Let's see the next one. The vector field XXX is independent of path. Okay, well, being independent of path means that you are conservative, correct? But if we take a look at the cross partials of these right here, we're not going to end up getting those satisfied. So for example, if we have P, Q, and R, we're going to do, say, QX, that should equal PY, but QX is 1, PY is 0. And 1 is not equal to 0 right here. All right, so that one is wrong. All right, so by process of elimination, we see that the last one is correct, but let's just see why it is in case we got stuck with some of these other ones. There is a vector field F on R3 such that the curl of F is 2x minus y minus z. Now, we had a problem similar to this earlier in the exam. Where was that? Was it that one? Yeah, it was this one. Yeah, so we had a problem similar to this earlier where we talked about the divergence of the curl being 0. And we also saw that the converse was true if we're on a nice space that's simply connected here. All right, so if the divergence is 0, then there is a vector field such that we're the curl of that. So let's just see if the divergence of this is 0. So the divergence of the curl of F is going to be 2. The derivative of the x derivative of this is 2, then minus 1. The y derivative of this is -1, and then minus 1. All right, so we do see that the curl, this could very well be a curl because the divergence of it ends up being 0 right here. All right, so there we go. That's why this one's true and then this one's false, because at least one of these is false right here. For A, isn't there also an equal number of vector pointing into the plane? So whether this flux is positive or negative depends on the orientation of the plane. So if the normal vector for the plane is pointing in the positive x direction, then it would have a very positive flux. But if the normal vector were pointing in the negative x direction, it would have a very negative flux. But in either case, it's either going to be very positive or very negative. It's definitely not going to be 0 right here. So you don't have to go find F by itself. You can just compute the divergence of the curl. That's right, because if it is a curl, if this is a curl, then its divergence should be 0. All right. Let's see here. Oh, wow, we're over time. Sorry about that, guys. All right, so that concludes this exam right here. So hopefully that served as some good practice. I want to remind you guys, don't be afraid of these guys. I know it's kind of intimidating because there's so many of them and we're still a little shaky on surface integrals and stuff, but I strongly encourage you to use these whenever you can because they almost always make the problem easier right here. So try to use these as much as you can. If you feel like there's a chance you could use one, see if you can. And most of the time it'll make your problem easier. All right, it's been good having you guys as a class, and send me any emails if you have any other questions. And I wish you all best of luck on your final exam.